Welcome to the last video lecture in this course. So today we'll be revising on the topic of counting. So combinatorics is a branch of mathematics that involves counting. It's a very big part of mathematics, and we have seen that big names like Ramanujan and many other people have worked on this particular field quite a lot. A typical question is, given a set S, what is the cardinality of the set S? Now the main question is, how is this set given? Usually the set is given in terms of words and you have to count it. For example, one can ask how many elements of a set satisfies a certain set of conditions. Or if you draw, how many ways can you draw an element from the set such that the element satisfies the set of conditions? There are quite a number of examples that we have already seen in this course. Now each problem is unique and each has to be solved applying a technique that fits it. In fact, combinatorics is possibly one of the most challenging subjects in mathematics, and hence some of the most creative ideas come out in the field of combinatorics. Some of the best work of Srinivasa Ramanujan was on counting. There are quite a number of handy tricks and tools that one can be used to attack these problems, and that's what we have learned in this lecture. In particular, we looked at two special cases. Case 1 was, how many ways can you select k objects from n objects? And the idea was that it all depends upon whether the k objects are or n objects are identical or not, whether repetition is allowed or not, whether the ordering once we chose it matters or not, and so on. And the other thing is that how many ways can you distribute n balls into k bins, and whether the bins are distinguishable or indistinguishable, whether the balls are indistinguishable or distinguishable, whether the matter ordered inside them matters, can the bins be empty? These are various cases that we handled, and by doing so we have come up with we kind of went through the whole of it. So we have looked at the various cases and we saw how to compute for each of the various cases. Now these are some small tricks that we use to solve these problems. But one of the more general techniques to solving the counting problem is using recurrence relations. Or in other words, recurrences is a very useful way in which the nth term is written as a function of the previous terms, and it has been extensively used for various other fields. So the main thing to study is that how to use recurrences to model problems and how to solve the recurrence relations. Now we have in fact seen quite a few examples of how to model problems using recurrence relations, and we also saw various techniques for solving recurrence relations. The technique that we have seen, the most obvious one was first guess the solution and then prove by induction. If one can guess it correctly, then that's it. But guessing the solution can be a tricky problem. So we have looked at a few techniques. The technique 1 was the unfolding the definitions, and we saw how this can be used to solve this or guess the recurrence relations. But then there are techniques where unfolding technique doesn't work. Problems or where unfolding techniques doesn't work. Particularly when the function that we guessed is very complicated, or when the recurrence relation is not that nice. So to handle the second case, when the recurrence relations are not that nice, what we did was that we can come up with upper and lower bounds, and maybe that would be good enough for us. And that introduced us to the field of asymptotic notations, which are an extremely important mathematical language for stating relationships between functions. It has been used quite extensively in algorithms and in various other fields also. We saw that how one can use the asymptotic notations to solve the recurrence relations, not exactly but asymptotically. For example, a problem like this could be solved using asymptotic notations and prove that Mn is theta of n log n. And again, the way to prove it is by induction. So all these things are basically somehow guess the solution and then prove by induction, either the exact value or the asymptotic value. But then there are other recurrence relations for which situations are much more complicated, and getting even an upper bound or lower bound is not good enough. And for those, we came up with a completely different technique. It's again an extremely powerful technique, and possibly the hardest things we have done in our course till now, namely which is called generating functions. So the idea is that if you have a sequence of numbers a0, a1 to a infinity, we consider this polynomial p of x as a0 plus a1x plus a2x square, and this is called the generating functions of this equation. And somehow, by using the recurrence relation, we can write the p of x as a function of x irrespective of all the ai's. We saw various examples of this one. And we use the concept of generalized binomial coefficient and the Taylor series that we have seen to solve them. So this was the techniques that we have seen for counting problems or combinatorics problems. To wrap up the whole course, we have covered in this course proof techniques, introduction to graph theory and linear programming, combinatorics, recurrence relations, asymptotic notations, and generating functions. Now let me be honest with you that whatever we did in this course is just a small part of what the actual course of discrete math is. Discrete math is the vast subject actually. I have only been able to introduce you to some of the subjects and show you the nice, exciting parts of them. There are lots and lots and lots of things to do outside whatever we have done. I pointed out to things like graph theory or generative functions and so on. And the world doesn't end there. Discrete math is the basic foundation for mathematics, basic mathematical foundations for whole of computer science, whole of various kind of part of mathematics and so on. So if you are interested in discrete math, please continue with your finding out other subjects that fall in this category and keep on reading them. Thank you.